Is there a secret government program that controls our clocks through the power lines? And why are power companies adjusting our clocks in the first place? Shouldn't it be a government time standard agency like NIST? On What's Inside today, I'm going to take apart my 1990s Radio Shack digital alarm clock and find out what's inside and how it keeps time, and if there is a timing chip in it, or it's somehow magically getting its time from the power companies. Alright, but first, before we take apart the clock and take a look at the innards, let's just do a quick web search on this to see if there's any truth to this, that our clocks are actually being set by the line frequency and not by a crystal or some other mechanism that actually makes sense. So yeah, doing a quick search of this, power line frequency is adjusted throughout the day to counteract daily fluctuations in electricity demand and to correct for timekeeping errors. Timekeeping errors. Process known as time error correction. So all the utilities in the United States still do this. They take a look at the 24-hour period. Well, we'll actually just head down to the article here. They take a look at the 24-hour period and make sure that it all adds up to exactly 24 hours. And if it doesn't, they manipulate the frequency the next day so that it does. So long-term, daily grid operators account for the cumulative effect of short-term frequency deviations over a 24-hour period. And some of them are as much as 20 seconds in some systems. So how crazy is that? This correction the next day involves a planned deviation in frequency. They just change the frequency so it's a little bit less or a little bit more so that the next 24-hour period accounts for the error and timing from the day before. Why is it important? Well, old style electric clocks like the one we're about to take apart use power line frequency to keep time. So we're going to crack it open. We're going to double check it and see what's inside and see if it has a crystal or some other time base internal, or it's actually getting its time from the power lines. All right, out in the Vtank we have my Radio Shack clock, 121 volts going into it, give or take a few, and 60 hertz as we can see from the meter. So question is it using that 60 hertz, 60 cycles to count for 1 second, and then increment the clock based on that? Or does it have something else on the inside allowing it to work? First step is I wanted to know the vintage of this clock. So I found it in a 1999 Radio Shack catalog. It's described as having a snooze button, UL listed, AC, battery backup, which I found interesting, battery sentinel just to tell you when the battery dies, etc. Catalog number is 63-796 for you Radio Shack aficionados. And you know you're out there, because I'm one too. This is the clock right here in my hands. I actually use it in my bedroom every night. Apparently I've been using it for 26 years now. Had no idea it was that old. Got all the standard equipment on it. It's got the alarm on and off, high or low for the display brightness. So that's nice. Hopefully you can see that there. Time, alarm set, minute, hour. And that's kind of it. Backside, QA passed. Looks like there's only a couple screws holding it together. I think I've been in this before because there's tape on the bottom. And here we are, 63-796, 1.4-inch LED alarm clock, manufactured for Radio Shack, a division of Tandy Corporation. And for the record, I only use this to see the time in the middle of the night. I have an Apple Watch for my alarm clock. All right, let's just take a quick look here. Here's the battery compartment. Does it in fact use a 9-volt battery? I do wonder if it will actually keep time when it's on the battery, or if it just maintains the last time. In other words, is there a timing circuit for when it's on battery to create a clock signal, if this is in fact getting it from AC and the AC is gone? All right, let's go ahead and peel that tape up off the side of it that's holding the bottom case on. My guess is, if I can vaguely remember right, I probably had it open and broke the lower plastic tabs. I mean, right now this plastic is, for the clock case, is about 26 years old, so a quarter of a century, which is crazy. AC is off. Go ahead and use my trusty screwdriver. Take out the 2 screws that I'm aware of. Alright, let's let's try to figure out how we're going to open this. Oh, that was it. That was easy. This pops up on the bottom. Well, that's probably because the tabs were broken off when I originally took it apart. A long time ago, though. Well, let's see. Just sort of pry it from the bottom here. See if we can get this. Oh, there it goes right off the top. Okay, nice and easy. All right, we got that open. This is the red lens that fits through there. Put that over there. That's the actual LED with dust on the inside, not LCD, LED. Big red honking LED. There it goes, just to prove that it works. It's red, but they have the red lens, I think, just there to keep it looking nice. So that's good. Defaults to 12 o'clock, which we're all used to. AC is off. See, we're going to have to take that display board off to get to it. So go ahead and just take the screws out of the display board. Looks like there's only 2 here. Nice and easy. I like that magnetic tip, by the way. It's pretty awesome. No idea where I got it. Oh yeah, and look at that. I cracked it before. I had to glue that back on. So, yeah, one problem at a time. There we go. There is the actual guts of the clock. Sorry the angles are off a little here. There's a piezoelectric. That makes the alarm. That's the speaker. And not a lot going on. I see resistors, diodes, capacitors. I see no crystal. I see this chip, an LM8560. Keep note of that. 3 transistors and a capacitor, another capacitor, diodes. Yeah, no timing circuit that I can see in here. So we have to look up this this chip set here. And underneath it, we've got this transformer, which is what takes the AC and drops the voltage down. Probably hits a couple of diodes to kind of make it a pseudo DC with a capacitor. That's probably good enough. A couple different leads coming off it, so I'm going to guess one of those leads is just a super low voltage timing lead that they're using. And here's the 9-volt battery leads that come in, so the 9-volt battery backup. So I'll be interested to see how they implement that as well. And we'll get some data on that in a few moments. So that's kind of the innards of this clock. So the real work is going to be on this 8560 integrated circuit and how it works and what it does. Okay, so the real work begins with this diagram that I downloaded off the internet, of course, for the LM8560. It's an out-of-date or no longer manufactured chip from Sanyo, so we're just going to take a quick peek in here and just comment on some of the stuff I see in the diagram. So let's see if we can scroll down. There we go. Alarm-equipped digital clock ICs with built-in drivers. So it can directly drive LED displays. That's what makes it really nice from a manufacturer standpoint. One chip, boom, done. Alarms, clocks, clock radios. Let's see if there's anything else good in here. Pinouts, taking a look at those. 12-hour, 24-hour select. I see 50 or 60 hertz, so that answers my question, even though I didn't see anything settable for 50 hertz. I bet they had a version of this for other countries that use the 50 hertz standard. Snooze input, sleep input, hour, minute. I don't know what the actual clock channel is, but we're going to find that. 24-hour control, AM, PM, built-in battery backup CR oscillator. So I find that really interesting that it has that for the battery backup, but yet it's probably just not accurate enough, right? It's probably not done with a crystal or anything like that. It's done with some loose time base. Equipped with power failure display function. I believe that's where it blinks on and off. Output for the alarm tone, 900 hertz, if you're ever interested in that. When the AC supply is interrupted, the time counter switches to a holding state and a built-in oscillator prompt begins operation. If the 50-60 hertz input continues for 3 clocks, I'm assuming that's 3 clock cycles without arriving, the oscillator's output is activated and functions as a time counter clock in place of the 50-60 hertz input. The frequency level of this clock oscillator is determined according to the CR value. Okay, well that's interesting. So that's good. So it does have, when it's in battery backup, it's got some sort of clock signal to it. But the rest of the time, it's getting it from the wall outlet. So that is completely bizarro world to me. Why not just build it all in there in the first place? So display modes, settings, controls, power failure detection display. We talked about that. When activated by drop-in power supply, all segments which are lit begin to blink. That's kind of cool. Alarm operation and alarm, snooze input, block diagram. See if we can see what's in here. Oh, that's just kind of ugly. 50, 60 hertz select. That's 50, 60 hertz. Not sure what that's about. Still not finding what I'm looking for. I'm sure it's in here, but better minds will have to figure that out than me. Clock radio applied circuit diagram. Okay, that's for a clock radio. Clock applied circuit diagram. Here we go. So it's really amazing. You can actually crack open a unit, find the chip for it, and find a whole circuit diagram of, approximately how you'd build it. So we got our AC coming in. It's hitting a couple diodes, obviously, right, to kind of give us that DC. Cycle 1, cycle 2, not sure what that's about. Here's the battery backup. Battery backup is actually protected by a diode. So you have the battery sitting over here on this side. And the diode will prevent current, it looks like negative there, current from flowing from the battery or flowing from the clock transformer into the battery, causing a hazardous condition. It only allows the current to flow to the clock. All your buttons on the top. Piezoelectric buzzer for sound, your LED display, and a 50, 60 hertz input. So that's its clock timing. It's got a 100K resistor there, 0.01 microfarad capacitor there. So it's just got a low level, low power, low energy circuit to the chip just to give it its 60 hertz input, which is actually its clock. So I find that interesting. I see AM, hours, set, nothing else. So that's kind of it. Okay, so that all that tells me is that we got 50, 60 hertz input from the spec sheet. What else? I saw some transistors in there. I don't see any transistors in this circuit diagram. I see 3 transistors in the clock radio circuit diagram, so I find that interesting. But when we cracked it open, we had some extra stuff. Electrical characteristics. All right, well, this is pretty boring, but here we go. Disclaimers, that would be about 100 pages these days, but back then they fit it into a couple paragraphs. So that's kind of it. All right, let's go ahead and get this clock back together. That is a spacer. I actually didn't notice it falling out, but I went back and reviewed the video and verified that it actually does fit right in that little spot. It literally just sits on top of the circuit board. There's no screws on the inner circuit board. It's just cables and wires, and as cheap as you could make it apparently. And it just sits there to protect the circuit board from shorting out on the transformer. Isn't that crazy that they would build it so crappy? It's a good thing they only had a paragraph of disclaimers for the chip. I bet the clock has even less. But as we know, Tandy Corporation, Radio Shack is no more. So I don't think they have any liability left. So in a nutshell, this is just absolutely crazy that, this is the clock, comes down to that chip. But really, every single day we need massive infrastructure, which is the power companies, to maintain 60 hertz and then go back and readjust the 60 hertz to make sure that by tomorrow when I look at the clock, it's still keeping time. And they still do it to this day. I can only imagine the expense to, if your clock functioned and the frequency is off just a tiny little bit, they have to go back and they readjust that later on. Absolutely mind-bogglingly crazy that even happens. Incidentally, I ran this clock on a UPS during an extended power outage, and the time actually does go a little wonky. The time base of those on a UPS or even a cheap generator are not very accurate. You know, they could be like 63, 64 hertz, 58 hertz, depending on the load, and that completely changes the clock. So this clock is no good without a good AC signal. All right, thanks for watching, and I hope you learned something here. I always find this stuff interesting myself. Again, I don't usually know the outcomes, so that's kind of the cool part of the whole thing. Please make sure to like and subscribe, and watch some of my other videos if you find these interesting. Thanks a lot, guys. Have a great day. Bye.